Good morning. Today we're going to talk about Math 101, Section 5.3, solving systems by the addition method. Now, the addition method is pretty much the preferred method. It depends on the problem situation you encounter. I think most times you'd want to try the addition method unless conditions indicate otherwise. All right, this topic should be familiar to you from your high school careers. I'm going to dive right in and do an example. Example 1 will still be dealing with systems. This is what I call a 2-by-2 system, two equations of two unknowns with two unknowns, and you're asked to solve both equations simultaneously. All right, if I add these two equations, well, I will get an equivalent equation, and I see here the plus y and the minus y will cancel each other out. If I add the x column, I'll get a 3x, plus y and minus y cancel out, and I get 3x equals 9, or x equals 3. Well, I'm halfway there already. If x equals 3, then I can plug into any equation I like. I'm going to pick the first equation, plug in the value of x equals 3. So 3 plus y equals 6. Subtracting 3 from both sides, I get y equals 3 as well. All right, so when I'm in this system, x equals 3, when y equals 3, let me go ahead and check this value. These pairs of xy values, oops, 2x minus y, sorry. This pair of xy values must solve both equations simultaneously. I don't insist that we check each answer each time. That may be a bit too cumbersome, but I will do it here for this system. All right. These values of x and y must solve both equations simultaneously. If I check the first solution, if x is 3 and y is 3, do I get a true statement? Indeed I do. 3 plus 3 equals 6. And in the second equation, I'll check that as well. I'll get 2 times x is 3 minus y is also 3. Is that equal to 6? 2 times 3 is 6. 6 minus 3, oops. Hang on a minute. It shouldn't be a 6 there. It should be a 3, right? Right? 2x minus y equals 3. Is this a true statement? 2 times 3 is 6, and 6 minus 3 is indeed 3. So we see this pair of values does indeed solve both equations simultaneously. Final answer, in ordered pair format, x is 3 when y is 3. All right, let's try another one. In example 2, in our text, this is on page 316, in section 5.3, we're given another system, x plus 3y equals 13, and equation 2, we'll call it x plus 4y equals 18. All right, essentially what you do when you solve with the addition method is rig things so that when you add the equations, you will end up canceling out one variable, and you will be left with one equation with one unknown, one variable, which hopefully we can solve fairly easily. So we're going to try to solve this by the addition method. Now, which variable you want to cancel out? Well, it depends on the problem situation. I imagine here it would be easier to cancel out the x values than the y values. If I take the first equation, equation 1, and multiply it through by -1, I get an equivalent equation. Right? Same solution set, but with a negative coefficient, a -1 coefficient in front of that x. Equation 2 I'm going to leave alone. Alright, so now if I add these equations, I'll get a resulting equation with only one variable, right? The x and minus x will cancel each other out. I'll get, well, 4y minus 3y is 1y, and 18 plus or minus 13 is 5. So right away, I know when y is 5 in the solution of this system, and again, I could pick either equation here and sub in y equals 5 to solve for the remaining unknown x value. All right, so I'll say, well, let me pick the first equation. I'll plug in y equals 5. All right, so x plus 3 times y, 5 in other words. X plus 3 times 5 equals 13. X plus 15 equals 13. Subtracting 15 from both sides, I'll get x equals minus 2. All right, so when y equals 5, x equals minus 2, and this pair of values will solve both equations simultaneously. And if you like an ordered pair notation, that's my solution there. All right, let's try example 3 in section 5.3. This is example 3 on page 317. And they say solve by the addition method. And the system is 2x plus y equals 11, and x plus 3y equals 18. All right, now you can see we're going to have to do some surgery here to get one variable to cancel out, and which variable you want to cancel out is it's a matter of taste, I suppose. Sometimes it's to your advantage to cancel out one or the other. Again, depending on the problem context. Our author chooses to multiply equation 2 by negative 2. All right, if we multiply equation 2 by negative 2, well, I'll have a negative 2x in the first slot, and that will cancel out the positive 2x in the first equation. All right, so let me go ahead and make a little adjustment here. A little surgery. I'll leave the first equation alone, and I'll multiply the second equation by minus 2. I'll abbreviate that minus 2 times number 2 in that fashion. That's my own notation, not the author's. I'll get a minus 2x, right? And minus 2 times 3y is minus 6y equals, and minus 2 times 18 is minus 36, right? All right, I now have an equivalent system. Number 2, the equation here, is an equivalent equation to the one I started with here. All right, so I can then add these equations and get a resulting simpler equation. Right? The 2x and minus 2x cancel out. Minus 6y plus y is minus 5y. And minus 36 plus 11 is minus 25. I'll divide both sides by negative 5, of course. Canceling the minus 5's on the left, I get positive y equals, and negative 25 over negative 5 is positive 5. All right, so I know that the y coordinate of my solution is going to be positive 5, and I can plug y equals 5 into any of the equations above to solve for the remaining x value. I'm going to pick the first one. If 2x plus y equals 11, if I let y equals 5, I'll get 2x equals, subtracting 5 from both sides, I get 2x equals 6, and of course, x equals 3. So y equals 5 when x equals 3. All right, so my solution in ordered pair format is the 0.3, 5. All right, example 4 on page 317 in our text right at the bottom. This is solve by the addition method, not surprisingly. All right. And we are given this system of two equations with two variables, two equations with two unknowns. 4x equals minus 2y minus 18, and minus 5y equals 2x plus 10. All right, notice these equations are not in the same format of the first three examples we did today. The first thing I'm going to do is transpose both these equations into standard form. Standard form, recall, is ax plus by equals c. In other words, a multiple of x plus some multiple of y equals a constant. In this way, the x's will be in the same columns and the y's will be in the same columns. Will make it easier to use the addition method. All right, so in this first equation, I'm going to add 2y to both sides. I get 4x plus 2y equals minus 18, transposing into standard form. In the second equation, the bottom equation here, well, if I subtract 2x from both sides, I'll get minus 2x minus 5y is already on the left side equals positive 10. All right, it's important to note this is an equivalent system. All right, we've transposed by doing algebra type things to the equations, balancing the equations by adding and subtracting items from both sides. All right, so same system here really in a different form. Most importantly, it's going to have the same solutions. All right, what are we going to do here? All right, our author suggests to take this bottom equation, multiply it through by positive 2, and then when you add it to the top equation here, you'll get a cancellation of the x variables. All right, so let me go ahead and do that. I'm going to leave the first equation, the top equation here, alone. 4x plus 2y equals minus 18. And downstairs, I'm going to multiply through by positive 2. That'll give me a negative 4x minus 10y equals 20. Again, same system with the same solution because I did algebra type things in balancing the second equation format, right? All right, I'm ready now to add these equations because I'll get a cancellation in the x variable. That's what I wanted. If I add the y values here, the y terms here, I'll get minus 8y equals, and on the right I get 20 plus minus 18 is 2. All right, I smell a fraction coming up here. Well, don't panic. Y then equals 2 over negative 8, dividing both sides by negative 8, which of course reduces to negative 1/4. Now, if your solution turns out to be a fraction, well, that can happen. Right? Sometimes we have to deal with the fractions. Right? So I'll say y equals negative 1/4. That's going to be half of my solution set. Now I have to find what x is. Again, I'll plug y equals 1/4 into any of these equations. Our author picks this one. All right. So plugging in y equals minus 1/4 for y here will result in the equation 4x plus 2 times minus 1/4 equals minus 18. And I can solve for x hopefully pretty easily. I'll get 4x plus, let's see, 2 times minus 1/4 is minus 1/2 equals minus 18. All right, I'm going to multiply both sides by 2 to get rid of the fraction here. 2 times 4x is 8x, plus 2 times minus 1/2 is negative 1, equals minus 18 times 2 is minus 36. Right, we're almost done here. So 8x, adding 1 to both sides, gives me minus 35. And x in our last step is minus 35/8. And that's already in simplest terms. All right, so when y is minus 1/4, x is minus 35/8. If you like, you can put your answer in ordered pair format. Notice both x and y values are fractional here, and that can happen sometimes, and when it does, we'll just have to deal with the hopefully not too cumbersome fractions. All right, we'll try example 5 in our text next. Example 5, this is on page 319 right at the top. And again, they give us another system. Solve by addition method. I'll abbreviate it this way. And here's the system. 2x plus 3y equals 6. And 5x minus 4y equals minus 8. All right. There's the system. All right, well, which variable are you going to try to eliminate? Here, we're going to have to do some double surgery because 5 is not a multiple of 2, and certainly 4 is not a multiple of 3. So to eliminate either of the variables, we're going to have to do surgery, some mild surgery, to really both equations here. Our author chooses to go for eliminating x. All right, if you want to eliminate the x variables, I suppose the easiest way would be to take equation 1 and multiply it by negative 5. I'll indicate it like this. 1 times negative 5. All right. If I multiply equation 1 by negative 5, well, I can write it as minus 10x. Minus 5 times 3y is minus 15y equals 6 times 5 is minus 30. 6 times negative 5 is minus 30. All right, if you want to eliminate x, well, then you should take equation 2 and multiply it by positive 2. Because 2 times 5x is going to be plus 10x. All right, so in the first slot, 2 times 5x is 10x, minus 2 times 4y is 8y, equals 2 times minus 8 is minus 16. Equivalent equations, equivalent system, same solution to both. Only in this system, when I add the equations, the 10x's will cancel out. 10x and minus 10x will cancel out. I'll get, well, minus 15y minus 8y will give me a minus 23y, right? Equals minus 30 minus 16 is minus 46. And I believe 46 is a multiple of 23. So if I divide both sides by minus 23, minus 23's cancel on the left, and I get positive y equals, and a negative over negative is a positive. 46 over 23 is, of course, 2. So y equals 2, and I'm halfway there. All right, now in any of the above equations, you can plug in y equals 2 and solve for x. All right, our author picks the first one in the original system. 2x plus 3y equals 6. Trying to get it all in one frame here. Our author picks the first one here to plug in y equals 2. So 2x plus 3y equals 6 when y equals 2. So 2x plus 6 equals 6. If I subtract 6 from both sides, I get 2x equals 0. And when I divide both sides by 2, remember that 0 over anything is 0. The 2's cancel out on the left. 0 over 2 is 0. Right, so when y is 2, x equals 0, and that pair of xy values will solve both equations simultaneously. And again, if you like, in ordered pair format, x is 0 when y equals 2. All right, one more for today. We'll do example 8. In our text, this is on page 320. Solve the following system using the addition method. Here's the system: 2x plus 3y equals 7. 5x minus 7y equals minus 3. There's our system, and we want to solve via the addition method. All right. Again, if you look at the equations here, 5 is not a multiple of 2, of course, and vice versa. And 3 is not a multiple of minus 7, and vice versa. So I'm going to have to do some double surgery here. In other words, do something to both equations to eliminate one variable or the other. Again, our author chooses, well, so this is somewhat similar to the previous example. The author chooses to eliminate the x variable here. And to do that, he multiplies the first equation through by minus 5. Just looking to make sure I'm not doing the same problem again. Minus 5 times 1, well, minus 5 times 2x is minus 10x. Minus 5 times 3y is minus 15y. And minus 5 times 7 is minus 35. So it's a little different than the last example. And if you're going to multiply the top equation through by minus 5, I would probably multiply the bottom equation by positive 2. That will give me a 10x in the x slot, minus 14y in the second slot, and of course 2 times minus 3 is minus 6 here. All right, so I've rigged it up with an equivalent solution, an equivalent system, so that when I add these two equations, the x variables will cancel out. Looks like I'm going to get something a little nasty here. Minus 29y equals minus 41. And if I divide both sides by minus 29, I get y equals positive 41 over 29. Right? All right, so if we then try to take this y value and substitute into any of the original equations, you're going to get something a little nasty here, maybe a little too nasty. I mean, 41 over 29 does not reduce, and it's kind of a nasty fraction. What our author does is they say go back to the original equations and eliminate the y variable, just like you eliminated the x variables here. The solution will still be valid. So let me go write this out. I'll say now, go back to the original equations and solve and eliminate the y variable to solve for x. And I'm going to need a new screen here. So I'll just remember that y is 41 over 29. Let me get a fresh screen. All right, I'm going to write the system again. 2x plus 3y equals 7. 5x minus 7y equals minus 3. We already know that y equals 41 over 29. All right, so I'm going to take the same system and I'll say now rig it so you can eliminate the y variable to solve for x. It's an alternative method, but certainly valid. All right, I'm going to take the top equation and multiply it through by, let's see, positive 7. All right, take equation 1 and multiply through by positive 7. That will give me the resulting equation 14x plus 21y equals 49. Again, the goal here is to eliminate the y variable, so if I multiply the top equation through by 7, I'd want to multiply the bottom equation through by 3, positive 3. So 3 times equation 2 will then give me 15x minus 21y equals minus 9. And then we've rigged things up so that the y variable would cancel out. Right? 21y and minus 21y cancels out. I'll get 29x equals 40. Or finally, x equals 40 over 29. All right, so when y equals 41/29, x will equal 40/29. And there is my answer. This nasty value with 2 cumbersome fractional values will indeed solve both equations simultaneously. All right, it's about a half-hour point, so we will call it a day. And this concludes section 5.3, solving of equations by the addition method.